You float in silence, utter, perfect silence. There's no starlight, no galaxies, no sound or temperature. You're suspended in something that isn't space, and yet you're here, somehow. It's a realm before realms, a moment before time. The clocks haven't started ticking, space hasn't stretched. There is no up, no down, no left, no right. Just a dense stillness, wrapped around a singular possibility. Something is about to begin. What if there was no such thing as before? What if this eerie quiet wasn't a pause, but the very absence of time itself? In this place, earlier and later have no meaning. Cause and effect are not yet born. This isn't emptiness, it's potential. Physicists believe that asking what came before the Big Bang might be like asking what's north of the North Pole. Time, as we understand it, may have started with the Big Bang itself. In other words, time and space didn't exist before it. They emerged with it. But that doesn't stop curious minds from asking, could there have been something else? A hidden dimension? A collapsing universe that came before? Or maybe a deep sea of quantum nothingness bubbling with chance? In this mysterious before, quantum mechanics might hold the key. According to this theory, even a vacuum, a place with no matter, no energy, still isn't truly empty. It's restless. It flickers. Tiny particles pop into existence and vanish again, like dreams forming and fading in an instant. Perhaps the entire universe began as one of these fleeting events. Imagine the universe in its tiniest possible form, compressed into a single, infinitesimal point. This point held everything, every atom, every galaxy, every dream, every memory that would ever exist, all in one spot, smaller than a grain of sand. And then, without warning, it expanded. Not like a balloon being slowly filled, not even like a bomb exploding. Faster than the speed of light, this cosmic birth was more like a snap of transformation. Suddenly, time began. Space unfolded. Energy surged outward. But right before that moment, just a breath before time opened its eyes, we are left with pure mystery. What was there? Was it something? Or was it nothing? Maybe the truth is stranger than both. Maybe what existed before time wasn't a place or an object, but a rule, a pattern, a law so deep we haven't discovered it yet. Some physicists believe that the universe didn't come from nothing because nothing, truly, doesn't exist. There's always some kind of structure, some kind of law. Even in the absence of matter, the laws of quantum fields, gravity, and time may still linger. And this suggests something wonderful, that the universe may not be a random accident at all. Instead, it might be the result of a deeper logic, a framework that reaches beyond what we can currently see or measure, something that has always been there, waiting patiently for the moment when reality would finally unfold. As you drift in this impossible space before space, picture it as a great still ocean, utterly quiet on the surface, but underneath, an unseen storm of probabilities, spinning and shifting, until, one moment, improbability becomes certainty. The Big Bang. But let's not leap forward too quickly. Stay in this moment just a little longer. The moment before everything, before galaxies, before even a single photon of light. Just stillness, and the feeling that something vast is about to happen. Prepare yourself. Let's begin. It begins, not with a sound, but with an expansion. No explosion, no fireball shooting outward through space, because there was no space, no outward to go toward. Instead, space itself, everything that could exist, begins to stretch. This is the Big Bang. But it's not a bang like we imagine. It's not even an event in space. It is the event that created space and time and everything else that would ever be. Roughly 13.8 billion years ago, the universe begins to grow from an almost impossibly small point, a singularity, into something larger. In the tiniest fraction of a second, it expands unimaginably fast. Temperature, over 1 trillion degrees. Conditions, so extreme that the forces of nature themselves, gravity, electromagnetism, and the nuclear forces haven't yet separated. Everything is unified in a strange, boiling simplicity. And yet, this raises a difficult question. How do we know? The truth is, we don't have a full picture. The first moments after the Big Bang, less than 1 trillionth of a second, are hidden behind a veil. Our current physics just breaks down. So when we say the universe began, we're also admitting how much we don't know. Scientists have equations, elegant ones, but they unravel at the beginning. When you try to push back far enough into that primal singularity, math gives up. Still, there are clues everywhere. Look out into the night sky. Those faint points of light? They're ancient. Some of them so far away, their light began traveling toward us not long after the universe itself was born. And there's something else, fainter still, stretching across the whole sky. It's called the Cosmic Microwave Background, or CMB. Discovered in 1965, this faint glow is the universe's baby picture. It's the light left over from just 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and light to finally move freely. It's everywhere, a quiet hum, a thermal echo of the beginning. But even before the CMB, the universe had stories to tell, stories that science is still piecing together. One of the big questions is, was the Big Bang truly the beginning? Some theories suggest it wasn't, that our universe might have emerged from something else. Perhaps a collapsing universe that came before. Perhaps a strange sea of quantum fields. Or maybe a transition from another dimension. In some models, the Big Bang wasn't the start of time, but a bounce, a moment in an endless cycle of collapse and rebirth. One universe contracts, another explodes outward. In others, the Big Bang might have been a fluctuation in an infinite, timeless vacuum, a random ripple that triggered an avalanche of creation. In this view, our universe is just one of many that flicker into and out of being, a lonely firefly in a field of glowing possibilities. Or perhaps we'll never know, because we are creatures inside the system, looking back through time, trying to understand the engine that started the ride. But the moment of ignition, it may be forever sealed from us. Still, that doesn't mean we stop searching. Today's cosmologists use powerful tools, satellites that scan the background radiation, particle accelerators that recreate early universe conditions, mathematical models that stretch logic to its limits. And every so often, a new discovery reshapes what we thought we knew. So maybe the Big Bang wasn't the whole story. Maybe it was just a chapter in a longer cosmic book, a page in an ancient cycle we haven't learned to read yet. Still, we know this much. Something changed. Something transformed from potential to reality. From simplicity to structure, from silence to everything. And you, here and now, are made of atoms that once danced in that fire. Hydrogen formed minutes after the Big Bang still floats in your breath. Stardust swirls in your bloodstream. Whatever the Big Bang was, beginning or bridge, It connects you to the deepest origins of the universe. You are part of that story, and it's only just beginning. Imagine holding your breath at the exact moment everything changes. Time has begun. The universe is expanding. But now it takes an unexpected turn. In less than a trillionth of a second after the Big Bang, something dramatic and puzzling happens. The universe doesn't just grow, it inflates. Not slowly, not gently, but violently, exponentially. This phenomenon is known as cosmic inflation, and it might be the most astonishing moment the universe has ever experienced. Why do scientists believe this happened? Because it explains so many otherwise mysterious features of our universe. First, the universe looks the same in every direction. Whether you look to the left, right, or behind you, space seems smooth, balanced, uniform. But how can that be? Light travels at a finite speed. If regions of space were too far apart in the early universe, they couldn't have communicated with one another in time to match up their temperatures and properties. Yet somehow, they did. Inflation solves this. Before inflation, the entire universe was small enough for different regions to agree on their state. Then inflation stretched that tiny uniform patch to enormous scales. What was once microscopic is now cosmic. And that smoothness? It stayed locked in. Inflation also explains why space is so flat. Not flat like paper, but flat in terms of geometry. In a flat universe, the angles of a triangle add up to 180 degrees, and parallel lines never meet. It's a cosmic balance, and inflation makes it happen. Imagine blowing up a balloon. The more it inflates, the flatter its surface looks to someone standing on it. Inflation blew up our cosmic balloon until it looked, well, flat. And one more thing. Inflation provides a seed for everything we see. Galaxies, stars, planets, us. Before inflation, quantum fluctuations, tiny, random blips of energy, rippled across the infant universe. Normally, those would be too small to matter, but inflation froze them. It stretched those fluctuations to astronomical sizes, turning them into the clumps of matter that would, billions of years later, become galaxies. So the reason we exist may be because the universe shivered and then stretched. But what exactly caused this inflationary burst? That's where things get even more mysterious. Theorists suggest that some form of exotic energy called the inflaton field dominated the universe in those first moments. This field held tremendous energy, which pushed space to expand at breathtaking speed. Eventually, the inflaton field decayed, releasing its energy into particles, light, and heat, what we know as the hot Big Bang. In this view, the traditional Big Bang wasn't the very first moment, but the moment inflation ended and our universe heated up. So, ironically, what we often call the beginning may really have been the end of an even earlier process. Some versions of inflation go even further. They suggest that inflation might not stop everywhere at once. In some pockets, it ends, and universes like ours form. In other regions, it keeps going. This idea leads to a grand and unsettling vision: eternal inflation, in which our universe is just one of countless bubbles in a foaming multiverse. Each bubble is a universe, each universe with its own laws, constants, and fate. And here you are, in one of them, floating inside a cosmic bubble that began with a flash of light and a burst of unimaginable expansion. It's humbling, isn't it? To realize that everything you've ever known, the stars, the oceans, the people you love, exists inside a universe that was once smaller than an atom, then stretched faster than anything we can truly imagine. So tonight, as you look up at the stars, or simply close your eyes and drift through the thought of space expanding, remember, it wasn't just an explosion. It was a transformation, an invisible force reshaping the entire fabric of existence. A great stretch that set the stage for everything to come. Now imagine, if you can, a moment before light, before atoms, before form, a universe flooded with raw energy, chaos vibrating in every direction. And yet, from within that chaos, something begins to stir. Not matter, not yet, but something stranger, a flicker of potential rising from nothing. Welcome to the world of quantum foam. At the smallest scale imaginable, far smaller than atoms, smaller than quarks, reality becomes turbulent. You reach the so-called Planck scale, where space itself flickers, twists, and trembles. Here, nothing doesn't mean emptiness. It means a kind of energetic restlessness. This is the quantum vacuum, a seething sea of uncertainty. Even in a perfect vacuum, particles spontaneously appear and disappear. They blink in and out of existence, borrowing energy from the void and returning it an instant later. It's called a quantum fluctuation, and it's not science fiction. These brief, ghost-like particles have been confirmed in experiments. They are real. Now imagine this happening not just on Earth, but in the very before of our universe, when there was no universe at all. Could our entire cosmos have been born from one of these fluctuations? According to many physicists, yes. The idea is bold, that out of this frothing quantum foam, perhaps eternal and timeless, there arose a fluctuation just large enough, just lucky enough, to trigger something extraordinary. A universe, a pocket of space where conditions aligned perfectly, where a fluctuation sparked a runaway chain reaction, leading to the inflationary expansion we just explored. Some call it the ultimate free lunch, an entire universe born from a random tremble in nothing. But here's the twist. This nothing wasn't truly nothing. It was governed by laws, by probabilities, by mathematics. In that sense, reality itself, before the Big Bang, wasn't a place or a thing. It was a set of rules, rules that allowed fluctuations, fluctuations that allowed space, and space that allowed everything else. Let's make that idea even stranger. In quantum mechanics, nothing is ever perfectly still. Even the most stable vacuum is constantly fluctuating. That means nothing can't stay nothing for long. It's a state of imbalance, a seedbed for surprise. From this viewpoint, the universe didn't explode into existence. It relaxed into being, like a ripple forming on a still pond that could never remain still for long. Think about this. The total energy of the universe might be zero. That sounds odd, but here's how it works. The positive energy of all the matter and radiation in the universe is exactly balanced by the negative energy of gravity, like two halves of an equation cancelling out. If the net energy is zero, then maybe the universe didn't cost anything to create. And maybe, in a quantum world, anything that can happen will happen, eventually, including the creation of a universe. You are the result of that flicker. Everything, stars, clouds, whales, cities, silence, emerges from a single, momentary imbalance in a vacuum that was never quite nothing at all. It's poetic, really, that from the quietest silence, the loudest explosion of being could occur. But that also means something else. If quantum fluctuations can create this universe, could they create others? Could there be endless universes, endlessly bubbling into being? This is the heart of the quantum multiverse idea, a vision where countless universes are born from the restless backdrop of quantum possibility. Some last mere instants, others, like ours, evolve expand, and grow ancient. Each one a roll of the cosmic dice, each one with its own rules. And we are one story among an infinite library. So when you close your eyes tonight, picture that trembling stillness, the vacuum that wasn't empty, the foam that wasn't solid, the nothing that held the potential for everything. And remember, your world began with a flicker, a ripple in the deep, a moment when the universe whispered, yes, now journey deeper, back toward the very edge of knowledge, where even our best theories begin to fracture. At the beginning of it all, before even a second had passed, the universe wasn't just hot. It wasn't just dense. It was so unimaginably compact that all the energy and matter of everything, every galaxy, planet, and particle, was crushed into a single infinitesimal point. This point is called a singularity, a place where our known laws of physics collapse, where gravity becomes infinite, where space and time curve so sharply that our equations break into silence. It's not that we don't understand what's happening. It's that the very tools we use to understand anything no longer function. In the realm of a singularity, time doesn't tick, space doesn't stretch, mass doesn't behave. Instead, everything blurs together in a stew of pure potential. Density approaches infinity. The temperature is so high it defies description. It's like trying to explain color to someone who can only feel, or to measure water with fire. Our familiar rules don't apply. According to the standard Big Bang model, the singularity marks the very beginning, a point of infinite curvature in space-time, a mathematical boundary beyond which there is no before. But is it real? Many physicists believe the singularity isn't a physical thing, it's a signpost, a signal that our current understanding is incomplete, a clue that the true beginning lies beyond our grasp, waiting for a more complete theory to bring it into view. Enter the quest for a theory of everything, one that unites general relativity, which governs large things like stars and gravity, with quantum mechanics, which governs the tiny world of particles and forces. Right now, those two great theories don't get along. They argue, they clash, and at the singularity, where the universe was both infinitely massive and microscopically small, they scream in contradiction. This is why scientists pursue quantum gravity, a new framework that could explain what really happened at the singularity. And it's also where bold theories come in. Some models suggest that the singularity never truly existed, that the universe, while incredibly dense, never reached infinity. Instead, quantum effects created a sort of quantum bounce, reversing a prior contraction into a new expansion. Others believe the singularity may be a gateway, not a beginning, but a transition point, the collapse of a previous universe, the throat of a cosmic wormhole, a place where time loops, folds, or even ceases to be meaningful. Even black holes, those mysterious objects scattered throughout our universe, offer clues. They too contain singularities, at least according to general relativity. And if black holes are like miniature versions of the Big Bang in reverse, then perhaps studying them could reveal secrets about the universe's origin. There's a poetic symmetry to this idea. At the heart of every black hole, a singularity, crushing inward. At the heart of the cosmos, a singularity, bursting outward. Are they opposites, reflections, or two doors leading to the same cosmic truth? Here's something stranger still. Time may not have existed before the singularity. In our daily lives, we think of time as a river, flowing, predictable. But the singularity suggests that the river may have had no upstream. That time, as a dimension, emerged only after the expansion began. In this sense, the question, what came before the Big Bang, might be meaningless. not because it's unimportant, but because before may not exist. And yet, we can't help but wonder, because we live in time, we breathe time, our thoughts and dreams unroll across time's arrow, so we yearn to trace it backward, to see where it began. But standing at the edge of the singularity, we stare into a kind of mirror, one that reflects not just the origins of the universe, but the limits of what it means to know. Still, don't be discouraged, because sometimes mysteries are not walls, they are invitations. The singularity doesn't say, "You cannot pass." It whispers, "Come closer, look deeper." It reminds us that the cosmos, our home, is not just made of stars and matter. It is made of questions. And you, drifting gently now through this thought, are part of the answer still forming. Let's float now through time, not forward, but in circles, because some scientists believe the universe doesn't travel in a straight line from beginning to end. Instead, it may breathe, expand, collapse, and then expand again. This is the idea behind the cyclic universe, a concept both ancient and new, imagined by early thinkers and revived by modern cosmologists. It suggests that the Big Bang wasn't a singular one-time event, but a bounce, one chapter in a never-ending story of cosmic rebirth. Picture this. A universe expands for billions of years, stretching wider and colder, stars burning through their fuel, galaxies drifting further apart, until eventually, the expansion slows. Gravity begins to pull everything back. The cosmos collapses inward, slowly at first, then faster, until it shrinks into a dense, seething mass. And from that contraction, another Big Bang erupts. A new universe is born. This theory proposes a cycle. Bang, expand, slow down, collapse, bang again. Perhaps this has happened forever. Perhaps it will happen again. This idea has its roots in both ancient mythology and modern mathematics. Hindu cosmology, for example, has long described the universe as cycling through immense periods of creation and destruction. And now, cutting-edge models from theoretical physics suggest the idea might have scientific merit. One such model is called the ekpyrotic universe, inspired by ideas in string theory. It envisions our universe as a 3D brain, short for membrane, floating in a higher dimensional space. In this model, our universe and another parallel brain collide at intervals. Each collision triggers a new Big Bang. In that view, our cosmos is not alone. It's part of a grander architecture where universes periodically bump together like ripples on an endless pond, creating new sparks of existence. Another version, known as the conformal cyclic cosmology, was proposed by the renowned physicist Roger Penrose. He suggests that what we call the end of one universe, where all matter decays and black holes evaporate into radiation, could seamlessly connect to the beginning of the next. In this elegant twist, the end and the beginning become indistinguishable. One universe fades into the next, like notes in a never-ending cosmic symphony. But how would we know? Are there any clues left behind from previous cycles? Penrose believes there might be. He points to faint patterns in the cosmic microwave background, subtle rings, circular imprints that he interprets as echoes from a universe before ours. These are controversial ideas, still debated in the halls of science, but they offer an exciting possibility: that the cosmos remembers more than we thought. If the universe is truly cyclic, it transforms our view of time. No longer a one-way road with a start and an end, but a wheel endlessly turning. A cosmic breath with a rhythm slower than stars, deeper than gravity. It also changes how we see beginnings. If there have been infinite Big Bangs, then there was no true first. No moment when everything suddenly began from nothing. Just a dance, repeating across eons. And if that's true, if our universe is part of an eternal rhythm, it raises deeper questions. Have the same galaxies formed before? The same physics? The same stars? Could we be living through a story that has played out countless times before, in countless variations? Or is each cycle unique, different universes with different rules, each one a new experiment in cosmic creativity? It's impossible to say for sure. What we do know is that the idea of cycles offers comfort, because even if this universe fades into cold, silence and darkness, it might not be the end. It might be the middle. And somewhere, sometime, the cosmos may inhale again. It may collapse, then spark, then grow. And in that next universe, the stars may shine once more. So as you drift off, imagine this grand breath, the expansion and contraction of all things. Not a single story, but an infinite melody, a universe with no beginning and no end, just rhythm. Close your eyes and picture this. Not just one universe, but many, billions, trillions, perhaps an infinite number, each one floating in a vast cosmic sea. Some are quiet, others are chaotic, some governed by laws similar to ours, and others by rules so alien we might not recognize them as reality at all. This is the multiverse. It's one of the boldest ideas in modern physics, and one of the most fascinating. It suggests that what we call the universe is just one bubble in a much larger cosmic foam. Each bubble a different universe, each with its own beginning, its own history, and perhaps its own version of you. The idea of a multiverse isn't just wild speculation. It arises naturally from several serious areas of physics. Let's start with eternal inflation, a theory we brushed against earlier. According to this idea, inflation didn't stop everywhere all at once. Instead, it ended in patches. In some regions, like ours, inflation slowed and cooled, giving birth to stars, galaxies, and life. But in other regions, it continues. Space keeps inflating, eternally. And within that ever-growing inflating space, new universes constantly bubble into existence. Each universe sealed off from the others, like islands in a vast and growing ocean. This is the inflationary multiverse, an endless generation of universes, each with different initial conditions, different particles, different outcomes. But that's just one flavor. The quantum multiverse arises from quantum mechanics, where particles exist in multiple possible states until observed. Some interpretations, like the many worlds interpretation, suggest that every possible outcome actually happens, but in a different universe. In this view, every time a particle chooses a path, the universe splits. You turn left, a version of you turns right somewhere else. You blink, you speak, you sleep. Each action spawns new branches. It's not just physics, it's a cascade of realities. And then there's string theory, each with different laws of physics, different numbers of dimensions, different values for fundamental forces. In this view, the multiverse is baked into the very mathematics of reality. And while these ideas are mind-bending, they do something beautiful. They help explain why our universe is the way it is. Why are the physical laws so perfectly tuned for life? Why do atoms hold together? Why do stars burn just right? If there are infinite universes with all possible variations, then perhaps we just live in the one where everything happened to fall into place. It's called the anthropic principle. We observe this universe because it's one of the rare ones where observers can exist. Not because it's special, but because it permits life. Still, these ideas are controversial, because we can't yet see or measure other universes. They exist beyond the cosmic horizon, perhaps forever unreachable. But even if we never contact them, the math suggests they could be there, and the implications are profound. If the multiverse is real, then our universe is not the whole of reality. It's a single page in an infinite book, one melody in an eternal symphony, one story in a library with endless shelves. And that's humbling, because it means our universe is not all that is, just all that we know. And there may be other versions of reality where everything we understand is turned upside down. Time could flow backward. Gravity might push instead of pull. Stars could be made of ice. Light might move in spirals. And in some of those universes, there might be versions of you. Not quite the same, not copies, but siblings in possibility, carrying out lives slightly different or unimaginably so. But no matter how strange the others might be, this universe is yours. This moment, this breath, this awareness drifting through space. You belong to this reality, with its stars and atoms, its spirals of galaxies and soft gravity. And even if there are other versions out there, you only live this one. So as you lie back, let your mind expand. Past the stars, past the edge of our universe, past the idea of everything. And imagine the multiverse shimmering like a field of bubbles in a golden sea, each one a complete cosmos, and each one proof that existence is richer, stranger, and more beautiful than we've ever dreamed. Now imagine we could zoom in, far closer than any telescope allows, not into galaxies or stars, but deep down, past atoms, past protons, past quarks, all the way to the tiniest threads that might be weaving the universe together. These are strings, tiny, vibrating loops of energy that could be the fundamental building blocks of everything, not made of anything smaller, not particles, but vibrations. This is the heart of string theory, a bold and still developing framework in theoretical physics. According to string theory, every particle you've ever heard of, electrons, photons, neutrinos, and so many more, is actually the same thing. A tiny string, just vibrating in a different way. A violin string can produce different notes depending on how it moves. In the same way, strings in the universe can vibrate at different frequencies to create different particles. Mass, charge, spin. These are all just properties of vibration. It's a simple idea, but it has enormous consequences. To work, string theory requires extra dimensions. Not just the 3D world we walk through plus time, but 10 or even 11 dimensions of space and time curled up in intricate patterns too small for us to see. Imagine each point in space containing tiny loops, twisted and folded like origami. These extra dimensions could help explain why gravity is so much weaker than other forces, or why particles behave the way they do, or even why our universe looks the way it looks. But there's more. From string theory emerged an idea called M-theory, which adds even more richness. In M-theory, strings are just one type of object. There are also branes, short for membranes. These can be two-dimensional, three-dimensional, or even higher. And here's where it gets cosmically exciting. Our entire universe could be a 3D brane floating in a higher dimensional space. Everything we know, galaxies, stars, trees, you, is stuck to this brane, like dust on a sheet. But there could be other branes, other universes, just a tiny distance away in the extra dimensions. If they ever collide, the energy from that impact could trigger a new Big Bang. In fact, some versions of the ekpyrotic universe model we explored earlier are based on this idea. Two branes crashing together over and over again, birthing new universes in the process. And so string theory doesn't just offer a theory of everything, it may also offer a story of many things, a multiverse woven from vibrating threads and shimmering sheets. Of course, these are still theories. Beautiful mathematics, yes, but not yet confirmed by experiment. No one has ever seen a string or a brain or touched an extra dimension. But string theory has already led to deep insights, especially in the strange realm of black holes and quantum gravity. One such breakthrough was the holographic principle, the idea that the universe, like a hologram, might be described by a theory on its boundary. Just like a 3D image can be encoded in 2D, perhaps all of space-time is a projection of something deeper. This idea gained momentum through the famous AD-S-CFT correspondence, where certain theories of gravity in a curved space-time can be exactly equivalent to quantum theories without gravity, living on the edge of that space. It's like saying, everything inside a room could be described by what's happening on the walls. This may sound strange, but it could be the key to uniting quantum mechanics and general relativity, the two great pillars of physics that have never fully agreed. And if we can combine them, we may finally have a path to understanding black holes, the Big Bang, and the structure of space itself. It's a towering dream, but also a gentle one, because it suggests something delicate, that the universe, at its deepest level, may be made not of hard stuff, but of vibrations, of loops and strings and pulses, like a great silent song, one where galaxies are chords, gravity is rhythm, and light is melody. And we, tiny beings curled on a blue world, are part of that music, notes within it, carried along its cosmic tune. So as you fall asleep, think of this invisible song playing beneath your bed, your skin, your breath. The song of strings, so small you can't see them, so vast they might be everything. And if you listen very closely, in the quiet between thoughts, you might just hear them humming. Let's shift from the smallest threads of the universe to the deepest pits, to places where space folds in on itself and time twists like a spiral, to places so dense, so strange, that not even light can escape. Yes, you know what's coming. Black holes. They are the ultimate paradoxes of the cosmos. Simple on the outside, terrifying on the inside, and wrapped in mystery like a cosmic riddle. They form when a massive star collapses under its own gravity. The outer layers explode in a supernova, but the core keeps falling, past atoms, past particles, down into a singularity, a point so small and dense that the known laws of physics break. Around that point is the event horizon, the boundary beyond which nothing returns. Cross it, and you're gone, falling forever into the unknown. From the outside, a black hole is defined by just a few numbers: mass, spin, and electric charge. That's it. Everything else, shape, history, contents, disappears. This is called the no-hair theorem. Black holes have no hair, no extra details. But what happens inside? That's where things get weird. According to general relativity, all the mass collapses into an infinitely dense point, a singularity. But quantum mechanics refuses to accept infinity as a valid answer. Something else must happen, but we don't know what. Some physicists think the singularity doesn't really exist, that quantum gravity, perhaps via string theory, smooths it out. Others think the singularity might be a gateway to another place, another time, maybe even another universe. Could black holes be portals? Could they connect two regions of space-time through wormholes, hypothetical tunnels that link distant points in the universe? If you entered one black hole, might you exit a white hole somewhere else? Mathematically, the equations allow it. But reality is more cautious. Most wormholes collapse too quickly to travel through. Still, in theory, the universe might contain shortcuts. Even more bizarre is what black holes say about information. In physics, information is sacred. It tells you what's happening, what could happen, what once happened. And for decades, black holes posed a terrifying question. If you throw information into a black hole, is it gone forever? Stephen Hawking once said yes, it gets destroyed. But that broke quantum mechanics, because in quantum theory, information can never truly vanish. This led to one of the greatest debates in modern physics, the black hole information paradox. Eventually, Hawking changed his mind, and physicists began to suspect that the information isn't destroyed, it's just scrambled. Somehow, it's preserved in the faint radiation black holes emit, now called Hawking radiation. But where exactly is that information? Is it in the radiation, on the event horizon, in some hidden dimension? Enter the holographic principle again. Remember that idea from string theory, that all the information in a volume of space could be stored on its boundary? Black holes helped inspire it. Physicists discovered that a black hole's entropy, its internal disorder, is proportional not to its volume, but to its surface area. That was shocking. It suggested that what happens inside a black hole might be fully encoded on its surface, like a hologram. Not just black holes, but perhaps everything in the universe. Maybe the entire cosmos is a projection, and we're living on the boundary of something deeper. This principle gave rise to powerful theories of quantum gravity, and it made black holes not just cosmic monsters, but cosmic keys. Keys to understanding how space, time, and gravity emerge from information itself. And in the last few years, a quiet revolution has begun. Physicists have discovered that entanglement, the strange quantum link between particles, isn't just a weird feature of the quantum world. It might be the very thing that builds space-time. That's right. Space and time might be woven from entangled information. In this view, black holes aren't holes in space. They're places where information is packed to the limit, where space-time itself begins to unravel, and where new physics is waiting to be born. So as you drift tonight, think of them. The quiet, dark hearts of galaxies. Black holes are not just devourers, they are teachers. They hide the most powerful clues about the universe's birth, death, and ultimate structure. And they remind us that even in the deepest darkness, there's still light escaping. Not as photons, but as knowledge, waiting to be unlocked. Close your eyes now and follow your breath. Each inhale, soft. Each exhale, slower than the last. In the stillness of your mind, picture this: a night sky stretching across eternity. Not just above you, but around you, on all sides. Stars scattered like glowing dust. And somewhere, quietly shining, is a galaxy so far away its light has taken billions of years to reach us. Now think about this. That light, the soft ancient glow from that galaxy, left before the Earth had dinosaurs, before mountains rose, before there was an Earth at all. You're not just looking at space, you're looking at time. This is one of the great truths of the cosmos. When we observe the universe, we're gazing into its past. That galaxy may not exist anymore, but its light is still whispering its story across the cosmos. So tonight, let's follow that whisper deeper into the concept of cosmic time. You see, time in space isn't like the ticking of a clock. Einstein showed us that time is relative. It stretches and bends. The stronger the gravity, the slower time flows. If you were to spend a day near a black hole, years might pass elsewhere. This is called gravitational time dilation, and it's not just theory, it's been measured. GPS satellites must account for it to tell us where we are on Earth. Without corrections for time shifting in space, your phone would get lost. Even velocity can warp time. A fast-moving spaceship would age more slowly than one at rest. In space, time is fluid, malleable. But there's an even more haunting idea: the arrow of time. Why does time seem to flow in just one direction? Why do we remember the past, but not the future? The best answer lies in entropy, the measure of disorder. The universe began in an extremely ordered state. Since then, disorder has increased. Ice melts, stars burn out, eggs don't unbreak. This flow from order to chaos gives time its direction. It's why you grow older, not younger. Why galaxies drift apart, not closer together. And yet, the laws of physics, the deep equations of the universe, don't care which way time flows. They work the same forward or backward. So why did time pick a direction? Why did the universe begin in such a low entropy, highly ordered state? Some think the Big Bang created time itself, along with space. Others suggest our universe is one branch in a much larger multiverse, where different bubbles of space-time bloom with different arrows of time. Still others propose a universe that contracts and expands forever, where time reverses at the midpoint, and now we reach another cosmic mystery. What is time, really? We measure it with clocks, calendars, and heartbeats. But what is it? Some physicists think time might not be fundamental. It could be emergent, a product of other things like heat, entropy, or information flow. Others think time is just another dimension, like space, and our sense of now is just where we are in that block. In this block universe view, past, present, and future all exist at once. You're not moving through time. You're simply tracing your path across a fixed landscape of moments. It's strange, comforting in a way, because in that view, every moment you've ever loved, every laugh, every hug, every bright morning is still there, always there, unchanging, eternal, waiting like a photo in a cosmic album. And yet, we feel time. We feel its passing, its flow. Perhaps the universe is telling a story. Perhaps we are the story. Because for all the vastness of galaxies and quantum fields, you, yes, you, are a part of this cosmic symphony. Every second you live adds a note. Every thought is a ripple in the great sea of time. Every moment is a miracle of physics. So as you drift into sleep, let go of the clocks and the calendars. Let go of before and after. Instead, float gently in the now, the soft unfolding moment that holds everything. Because maybe, just maybe, that's all time ever really is.